We laid the groundwork the past few days to first grow the pebbles in the disk, and then we saw how then through the pebbles you can form the first planetesimals. So yeah, we are here then at this stage. So growing the dust, right? You start from the disk, you have the dust here in the disk, you grow this dust into the pebbles, and then we found a mechanism. We discussed a mechanism by which these pebbles, even though they're drifting through the disk, right? They are growing through barriers, such as the drift barrier and the fragmentation barrier. There are still mechanisms by which they can grow. We saw the streaming instability. You form the planetesimals. Question is then, what happens next? Now we are in a disk that has a lot of 10 kilometer, 100 kilometer bodies. These are the planetesimals. Somehow they must keep growing to form the planets that we see. So we are somewhere here then in this region. Today we're going to talk about planetesimal and pebble accretion. Right? So these are two main growths of, two main processes by which the planets grow. This suggests a reading I'm putting here. These are 3 very interesting reviews that came out in the past 7 years. Hansel and Lambert's here, 2017, Ormel, 2017, and this one that is on protostars and planets, 7, Troskowska et al. Right. So this is the stage, right? We have that, this is a version of that plot that I showed the last time. You have here the distance to the star, and here is the size of the grains, right, that are growing. And then three particles that are being integrated then in this disk that have different fragmentation thresholds. So this one has 1 centimeter per second, right? So they're only going to grow up to this point, and they're going to be bouncing off each other. This other here too has a threshold of 1 meter per second. So this is the fragmentation threshold for this one. 10 meters per second. You have this fragmentation threshold up here. So of course, because you can grow further up. So this would be typical for a silicate grain, and this would be typical for a nice grain, and this is the drift limit, right? And when we see what the evolution of the dust in disks are, I mean, what the evolution is, you see that there is a clear decay here in time as you pass here from early disks. Right? So these are the class 0 disks to class 1, and these are several class 2 disks to then class 3 disks and debris disks. So this evolution is consistent with these disks losing at about 100 Earth masses per million year, which is consistent with the pebble flux that we expect from radial drift. So this idea that there are pebbles in the disk and that they are drifting inward seems to match what the observations of the disks are. Right? So that's the situation that we are at then. We have that the planetesimals are forming, right? And then we have to find then a way to make them grow. The first thing that you can think of would be, all right, you have planetesimals in there. They are going to collide with each other, right? And then by this way, you can make the cores grow. That is the core accretion model via planetesimal accretion. This is the paper that laid it out to the foundation of that, Pollack et al. 94, see a classical in the field. What you're seeing here this is the result from one such calculation. You can start from several planetesimals all over the place. This is kind of cheating a bit because there is a Jupiter here, right? So as you can see, what is going on is that the planetesimals that are formed initially, they are in their orbits, they get stirred, and then they start meeting and merging. The eccentricity goes up. This is so some major axis and eccentricity. And then they meet, collide, and then keep growing. Eventually, you're going to have a few planets in there. Right. Right. It's a similar calculation. How we can start them from planetesimals to forming planets. after some time. Yes. Oh, the colors here is the water fraction. Yes. Yeah, you have here dry planetesimals are the red ones, and water-rich ones. Yeah, this model here had a nice line somewhere in the asteroid belt. Yes. Right. Well, yeah, it's not liquid, but that's ice. Yeah, the color code here is the mass fraction of water. All right. In any case, what I wanted to show here are the rates by which they grow. So today we're, in this first part of the lecture, we're going to see planetesimal growth. Planet formation by planetesimal accretion. And we're going to talk about, we're going to derive what the growth rates are, and then when that growth stops, which is the isolation mass. After that, then we're going to talk about pebble accretion, which is another way then to grow the cores. And maybe these two processes can be concurrent, or then one of the two can dominate. So the very first thing, then, how can we grow these objects? You have that, what is going on is that you have a mass here, a mass m, and it's orbiting, right, and then sweeping through this sea of planetesimals. Question, and what is the growth rate that you can expect from this? If you have this body of mass m and is embedded, right, in the swarm of planetesimals, you have that it is going to grow in mass by just the volume, right, that it sweeps times the density of these objects that it finds in its way. The volume, you can see it from there. You can approximate, you can write it in terms of the cross-section, which is sigma, right? And then the speed, the v, right, the velocity by which it goes through the medium, and dt. So this gives you the volume and then the density, right? So if you divide it by dt, then you have the mass accretion rate, right? Quite simple estimate here. So the growth rate of a planet, right, that is going through this planetesimal swarm is going to be given by this. So the speed that is growing, right, that's the orbital speed. The density is the number density of the planetesimals are in this volume. What is different here is what the cross-section sigma is, right? So the cross-section is not simply the geometric cross-section because it is augmented by the gravity, right? So for the cross-section, what you're going to find is that the cross-section is going to be augmented. So you have the geometrical cross-section of the planet. However, you're also going to be augmented by the gravity. So the escape velocity from the planetesimal, from the embryo that is trying to grow, and is augmented here by this factor, which is also given by the RMS speeds of the planetesimals. This comes from a simple gravitational focusing calculation. I'm not going to go through the algebra here, but that's what you get from this. Now you can plug in these quantities for, say, the density now. You can plug this in here. And then for the density, let's say that the density then will be given by the column density sigma of the planetesimals divided by the scale height. So twice the scale height of these bodies. And this is the scale height of the planetesimals, right? So that scale height is actually also going to be given by the RMS of the distribution. So let's give here an HP for a P index to this. That's the scale height of the planetesimals. It's given more or less by the RMS of the distribution over the Keplerian velocity. So, sorry, h over a here. So that's the aspect ratio of the distribution. So if you plug this in, then you find that dt, the accretion rate, is going to be given by the column density of planetesimals. Here, then, you can write Vk, right? So Vrms. If you write here Vk as omega times r, then you can cut the r from both sides, and then you have the Hp, the scale height of the planetesimals, is given by Vrms over omega. Put this here, then you find omega pi r squared 1 plus square of the escape velocity over the square of the RMS speed of the distribution. And this is the simple core growth equation. All right. Right. So we can simplify this. Let's call this quantity here F. And we can solve this for a simple model. Let's assume then that this is going to be constant. That's not always going to be the case, but if we make this quantity here constant, we can easily integrate this, because then the equation that we have is dm dt equal to sigma omega pi r square f. Here, then, you can write m as the density of the body. So m here for the density of the mass times the cube of the radius. And you can see what is happening here now. Plug this back here, then you have an equation for the growth of the radius of the body. All right. So there are some quantities here that you can already cut. You can cut the pi here. There's an r square. You can cut that too. So what you have is something quite simple in the end. The RDT, you have an equation for the growth of the body. This would be rho m. And everything here is constant, right? The column density is constant, the Keplerian frequency is constant. We assume that this quantity is constant, the density of the body also, so constant. That means that the radius is going to be proportional to the time. It's going to increase linearly with time. If you substitute some values here, you find that the growth is about 1 centimeter per year, which is quite slow. It would take about 10 million years for the objects to grow to 100 kilometers. However, that growth here depends also on the factor. I assumed here that the column density of planetesimals would be about 10 grams per centimeter square, times also this f. So if this quantity here f is 1, that's the growth rate that you get, which is quite slow. However, you can see here, if the RMS of the distribution of planetesimals is low, this factor f here can go up quite a lot, right? In any case here, what you have is, say that you can have this factor f. If you have the escape speed being much, much, much bigger than VR mass, then this f factor here becomes simply this term here. We can discard the 1, and then the f factor becomes 2gm over v square RMS over r. So v square here, so this is simply the square of the escape speed, 2gm over r. In the case where you can drop it that 1 factor, that's a good approximation for f. If you plug back this then into the equation for growth, plug in there, then what you find is dm dt is equal to sigma omega pi r squared, and then times this factor. So times this factor 2gm v square RMS and r. Okay? So cut this r here. Yes? What is a factor 2 between friends? You know? Right, where? Here? Yes. Yeah, this tree here is cutting. Yeah. Okay. All right. So there's a factor 2 here somewhere. Good. That's fine. Yeah. If you find that, let me know. Where should I put the factor 2? Should it be here? Should be 4. Okay. Yeah. Good. Thank you. Right. So let's cut these R's here. Right. Right, so let's now substitute the r here by this equation. We can relate the radius to the mass, right? So substitute r here by a function of the radius, so the cubic root of the mass. And then what you have then is an equation where everything else is constant, except for the mass here. So you have the mass, and this radius is going to contribute m to the power of 1/3. So m to the power of 4/3. Let me write this better because this is the result that I was going to show. So if you have this, you find that planets should be growing at a fast pace. Right? M here to the power of 4/3. That means that a planet will attain an infinite mass at a finite time. Right? This is a near exponential growth. This is what you find here when you integrate these equations. The largest body is growing the fastest, as you can see here, because the higher the mass, the higher the growth rate, right? The MDT is proportional to a high power of the mass. So the largest objects, they grow the fastest. Now, there is something off here. This growth cannot really continue in this way. What happened is that we assumed here that this f was constant, right? And that we are in a situation where we can ignore this term here, v escape being much, much bigger than v RMS. However, as a body grows, what is it that we saw in the simulation? That it's going to stir up the planetesimal disk. So as the bodies grow, so grows the VRMS of the distribution. And then that assumption is going to break down. So this here is a good approximation if the RMS of the planetesimal distribution is low, right? So the planets will grow, but as soon as they stir up the population, this approximation breaks down and you cannot use this equation anymore. So what can you use them if the distribution is dynamically hot? So V escape being much, much less than V RMS, I mean, being much, much more, that means that the population is dynamically cold. But as VRMS becomes big, you have a dynamically hot population. So this is for dynamically cold. And you can find what the opposite limit is. What is the equation for a dynamically hot population? I'm not going to redo the algebra here, but you can do that by simply applying the opposite limit when VRMS is much, much bigger than this, right? Then the V escape. So this term here goes to 0 and F goes back to being 1. What you have then in this case, so let's divide here both by 1 by the mass. What you have then is that 1 over m dm dt for the dynamically hot is k m to the power of 1/3, right? So the biggest body grows the fastest. That's for the cold one. But for the dynamically hot, if you play the same game and find what the equation is, you're going to find dm dt being k to the power minus 1/3. So in this case, the biggest object grows the slowest. So the situation here splits neatly into these two regimes. You have the regime of low RMS, right, which is for the dynamically cold. So that's this one here. The growth then is going to be proportional to the mass to the power of 1/3. That means that the largest body is growing the fastest, and then you have a runaway growth, right? The radius increases with time, and the fastest objects grow, and the largest body grows the fastest. And then in this case, if you have the VRMS being large, that quantity F there is going to be close to 1. And then the equation that you have is m to the power minus 1/3. That means that the largest body here is growing the slowest. You stall the growth. So the situation is here. You have one object growing quite fast. As it grows, it stirs up the soup, right? It becomes dynamically hot. It stalls the growth because this VRMS here grows, right? And then you end up with a few objects only. So you can divide the growth then in these two regimes here. So first you have only dust and the smaller planetesimal, so that would be orderly growth. The runaway growth then as the most massive object grows the fastest, and then its gravity will stir up the population, and growth then will stall with a few massive objects, and that's the oligarchic growth. This grows until the massive objects secrete all of the planetesimals in its orbit. We call that the isolation mass. Quite simple to find what the isolation mass is. You what you do here for the isolation mass is simply get the feeding zone, the width of the feeding zone, and equate the three masses. Equate the mass of the feeding zone with the mass of the planet that is growing. It's just the mass that the object would get if it accretes all of the planetesimals in its orbit. And then with this model, you can calculate what the growth rates are. And these are the tracks then that you get for the growth of Jupiter, where it is. And it seems that you get something that grows within the lifetime of the disk. So that was the conclusion from this article here. So you have the phase of the growth of the core. That's the solid line, right? The mass in Z, here Z being the metals in the disk. And then you have a slow phase here of accretion of gas, right? XY here is the mass of hydrogen and helium. And then when these masses become comparable, when you have about the same mass in gas as you have in the core, then you end up with this phase, this rapid phase of gas accretion here that completes the formation of the gas giant. So always fine and good when you apply this model to Jupiter. However, you start seeing here that already applying this model to Uranus, you end up with a long phase of growth here for the core, right? That is a big problem of this idea of growth by only planetesimal accretion, is that it seems to work up to about 5 AU. You can use that to explain Jupiter where Jupiter is. However, if you try to use that to explain anything beyond Jupiter, it fails miserably, right? So planetesimal accretion works up to 5 AU. And there was a problem in the field for a long time to find a way to make planets grow beyond 5 AU. You see here the formation of Uranus, where Uranus is, right, at 20 AU, already would take too long, right? More than 20 million years, which is longer than the lifetime of the disk. If you try to grow Neptune, if you put that to 30 AU, the accretion rates are going to be so slow that you can wait a Hubble time and not end up with Neptune. Right? So we need to find ways to make planets grow. The problem with this is that planetesimal accretion is inefficient because you are dealing with a problem that is conservative. It's just gravity. The capture radius for planetesimals is just too small, right? You have here this illustration. You have the object that is trying to accrete. A planetesimal here is passing, is simply going to be scattered. It has to get very close to the planet for a planetesimal to get accreted, right? The gravitational cross-section is just too small. In red here, this is the Hill radius, which is the gravitational reach of the planet. The Hill radius is, let me just put here because we're going to be using that. Out to the top is the semi-major axis of the body, the mass of the body times 3 times the mass of the star, and the cubic root of that. So that is the distance by which the gravity of the planet dominates over the gravity of the star. So a planetesimal has to get quite deep into the gravitational well of the planet, right, to be accreted. If it only enters the Hill radius, but not this gravitational cross-section, accretion is not going to happen. So how can we accelerate the accretion of planets? Actually, I stumbled upon that in a paper back in 2008, seeing here that there was a planet in this calculation growing very fast. So it's the maximum mass here in terms of the mass of the Earth. In less than 100 orbits here, this is in units of orbits, this object was growing almost to the mass of the Earth. And then when plotting what was happening here, you start from some objects here of a centimeter to meter size. Here is the first time that this would collapse, and this mass, this unit here, this number is in units of the mass of Mars. So we form an object here of 0.4 times the mass of Mars through direct gravitational collapse. And if the planetesimal accretion model is right, it would take millions of years for this object to grow appreciably, but in less than 10 orbits after, the mass was doubling quite quickly. And then you end up with an object of twice the mass of Mars. So the doubling time here was quite fast, right? You can guess what was happening here because this object is forming in a sea of pebbles. So it is accreting through them too. So you have accretion of planetesimals, but you also have accretion of pebbles, right? And which one of them is going to dominate was worked out then in this paper here. Yeah, Lambertsen, Johansen, 2012. What is going on here is that it's much easier to accrete the pebbles than to accrete the planetesimals because the pebbles are feeling gas drag. So for them, the motion is dissipative. Right? If you have gas drag, the pebbles, as they enter the heliosphere, they are losing energy to gas drag. It's much easier to accrete them than it is to accrete the planetesimals. The mass accretion rate, then they shoot. I mean, they grow up. I mean, they go up vertiginously here. So this is a calculation that they did. So you have the pebbles there. Soon they're going to switch on the mass in the center, and you see, like everything gets accreted like a vacuum cleaner. The mass accretion rate that you get from this is gigantic. It's about 4 orders of a magnitude larger than the accretion rates that you get from planetesimal accretion alone. So this has been a game changer in the field. So let's understand what is happening here. You have here that these are 4 different trajectories, right, or cases where pebble accretion may or may not happen. First here in this case, you have an object of low mass, right? So the only cross-section to accretion that it has, it's the geometric cross-section, right? So only the pebbles that are directly hitting it would be accreted. The cross-section here is small, so therefore the mass accretion rate in this case is also going to be quite small. And this then is what would happen if you have particles that are just too well coupled to the gas, right? So the particles are so small that even if they get very close to the planet, they don't get accreted by it because they cannot decouple from the gas, right? So these are different regimes of accretion. And then you have here an optimal case, right, where the pebbles are entering the heliosphere, and the ones that are within this cross-section will be accreted by the planet, and the ones that are not will be just scattered away. So that is a case where the accretion rate will be larger, and then in this case here, several of the streamlines here don't lead to accretion, right? That's the case of simple scattering by the protoplanet, and so that's the planetesimal case. The case where you accrete the best is of course this case here. So that's the case of pebble accretion. The accretion rates that you get from this are calculated, are shown here in these 2 plots. This is the Stokes number, right, of the pebble. If you remember it from last class, the Stokes number was the friction time normalized by the Keplerian frequency, right? So it's a known dimensionalization of the friction time and therefore how big the dust grain is. Usually, you'd think, usually Stokes number 10 to the -2 are millimeter grains, right? And so bigger sizes on this side and smaller sizes on the left. So this is the onset of pebble accretion, right? The axis here is the size of the embryo, the planetary body that is doing the accretion. The size here, and then the same thing translated to mass, assuming a density of about 3 grams per cubic centimeter, right? What you have here are different regimes of accretion. So the onset of pebble accretion happens here. So beyond that, you have essentially a planetesimal accretion problem. As you see here, the mass accretion rates for this case are very, very small. As you start on the pebble accretion trajectories here, the mass accretion rate goes up by a lot. And there are different regimes of growth here. So we call this the Bondi regime and the Hill regime, and the 3D or the 3D cases, and I'm going to get to that, what I mean by this. This plot here showing the maximum mass accretion rate essentially is collapsing this axis here, right, to just the mass of the body and the mass accretion rate. So it's kind of the same information, but showing here the biggest mass accretion rate for a given Stokes number here from this plot. And what you see here are the three regimes quite clearly spelled out. So this is what is measured from the simulation, right, the purple line. And in blue one, you have the planetesimal accretion growth rate. So that's the focus. So the accretion aided only by gravitational focusing. The red line is the line here from Bondi accretion. And the orange line here, the yellow line, is the accretion by Hill accretion. So as you see here, in this regime, the red line is very well reproduced, and then here you pass it then to the Hill regime. Essentially, the transition from Bondi to Hill happens more or less at the same as the transition from 3D to 2D accretion. And let me explain what I mean by these different regimes. So when a body is traveling through a medium, you have the classical Bondi accretion case, which means that the objects, if you're talking about gas, in that case, that would be the molecules of the gas that would be accreted by the body. The Bondi radius gives you what is the radius by which these are, actually, that would not be a square root here. You get the Bondi radius by equating the escape speed to the sound speed, right? So that would be gm over sound speed squared. So the case that we have here, it is not gas, it is pebbles, right? You have that the object is traveling through pebbles and is capturing them according to the Bondi radius that you would have not due to the sound speed, but by the shear. So you replace here the sound speed by the shear, so dv squared. So that's the difference in speed, right, between the gas and the pebbles. Remember that from last class, the gas orbits at a speed that is slightly sub-Keplerian, right? Where this eta here is given by the pressure gradient. Eta is 1/2 of the scale height of the gas over radius, right, square, and then the radial pressure gradient here. This would give you a small reduction, as you see, because it depends on the square of the aspect ratio, whereas the dust grains, let's call it V dust, orbit with the Keplerian speed. So delta V here, which is the velocity of the dust minus the velocity of the gas, is given by eta times the Keplerian speed. Right, so just get this here, divide by this, and subtract this. You end up with simply eta Vk. eta being of the order of 10 to the minus 3, you end up with a delta V of about 50 meters per second, as you saw last time. So that's the speed that goes into this Bondi radius that you see there. So the Bondi radius for pebbles is not the same one as for the gas. It's going to be gm over delta V squared. Right. So these are the two regimes, or three actually, that we have here. So it depends essentially on these three radii and which one of them is the biggest. If it is the capture radius only through gravitational focusing that you see there, right? That cross section that I wrote there in the beginning of the class, the Bondi radius, which is this one, or the Hill radius. So let me highlight this here. We have three regimes of accretion here: gravitational focusing, Hill radius, and the Bondi radius. Compare them, see which one is the biggest, and that's going to give you the accretion regime that you are at. Now, there is another length here, which is the scale height of the pebble disk. Now, that, if you remember from last class, also depends on the diffusion. Right? Remember that I showed that last time. We were calculating what the response of the pebble, so the gravity of the star would be. And we saw that the different pebbles of different sizes, they would settle to the disk with different heights. This one, right? This is a calculation here where you have pebbles of different kinds. They settle at different heights. In general, the scale height of the dust is going to be given by the scale height of the gas. But no. But multiplied by this quantity here. Alpha is quantifying the diffusion, right? So the RMS of the gas here squared is alpha times the sound speed, right? And ST here is the Stokes number. So you can see already from here some of the limits. If you have alpha equals 0, that means no turbulence, then HD is going to be 0, right? What does that mean? With no diffusion, there is nothing to stir up the dust. So it will settle then to the mid-plane with a scale height equal to 0, right? What would happen then for other limit? Let's see. For Stokes number equals 0, you see here, that's going to be 0, so this is going to give you 1. That means that the scale height is going to be just the scale height of the gas. That means very small dust grains do not settle down at all, right? They are just mixed with the gas. And another limit then would be for Stokes number infinity. For Stokes number infinity, again, the scale height would go back to 0. That means too big grains, they don't feel the gas drag. They just settle down to the mid-plane as if the gas was not there, right? So this is the limit of no diffusion. Everything settles down to the mid-plane. Very small grains, they just mix all over. Very large grains settle down, right? So that's what you're seeing there for different particle sizes. So you have to compare these when you compare the Hill radius or the Bondi radius or whatever radius is doing the accretion, if they are going to be bigger or not than the particle scale height. Because if it is bigger, if the cross-section of the planet is bigger than the scale height of the grains, the regime that you are at is going to be to dimensional, right? In this case here, I'm illustrating a case where the Bondi radius is smaller than the pebble scale height. So therefore, this accretion is going to be three-dimensional, right? You are offering the whole cross section to the pebbles, and then you have a three-dimensional accretion. But in the Hill radius case that is being shown here, the planet, as it orbits through the gas, it is seeing the whole dust layer as a single line. So that is a 2D accretion. That's what is being shown here, right? This is the mass of, this is the transition from the 2D regime for large masses, and the 3D here for low. And this is the mass of transition between Bondi and Hill. As you see, they are not exactly the same, right? But they're close in mass. Rule of thumb: low mass objects, they accrete in the Bondi regime and in 3D, and large objects accrete in the Hill regime and in 2D. Right? So these are the lines that you see there. Yes. Of the metallicity? Dependent? No, it's not actually. It does matter. The metallicity matters because it's going to give you how much column density you have. Essentially you can substitute this sigma here. Okay. Yeah, let me give here subscript D for dust. Everywhere that you see this sigma, you can substitute this sigma dust here by Z times the sigma of the gas. So the column density of the dust is the column density of the gas times the metallicity. This number for the sun is 10 to the minus 2, right? If you go back to the cosmic noon here, the redshift that Filippo has been teaching you, the metallicity can be quite low. Think that the metallicity around the cosmic noons, like redshift 3, was what, 10 to the minus 3 or 10 to the minus 4?
5, right?
I don't know if it goes all the way to 10 to the minus 5, but it can be quite low. So essentially, all of these equations here will scale with the metallicity. That is true. Yeah. Because of course,
you didn't mention the tides from the star. I mean, the star is not important for you.
The tide is in here. So
that's
the heliosphere. Yes.
Okay, good.
You find this radius here by equating the gravity of the planet with the tide from the star, right? Yeah. So the Hill radius is the distance by which the gravity of the planet dominates over the gravity of the star. Right. Okay.
So can I chime in?
Of course.
So a curiosity. Then is it fair to say that basically all planets in the, say, core have the same metallicity? The difference in composition boils down to how much gas they manage to keep? No, that's not correct.
No, it depends. Well, I mean, the location where planets
can make metallicity varies a lot.
Yeah. So even in the same disk, planets can form with a different composition depending on where they form, because different species will be either in the gas phase or solid phase. Yeah. Right.
So, I mean, in the gas phase, you can have a lot of non-metal.
Exactly.
I mean, a lot of metal.
Yeah. Metals and also non-metals. Indeed. Okay. Right. So let's continue here. So you can see here what the mass accretion rates are. For the 3D case, as I said, the cross-section is the full cross-section, right? That's pi r squared. And then you have here the dust density, and then the difference in speed between gas and dust, right? Delta V. So you can get here this mass accretion rate for the 3D case. For the 2D case, it is just a line. So the cross-section here is 2 times r, so that's the diameter of the radius that is doing the accretion, be that the Bondi radius or the Hill radius. And now it is accreting from the full column of dust. So that's here why it is sigma d and not rho d. And again here, delta v. So that seems to be all good and fine. Now let's apply this then to a problem. So in this next minutes, in this next few minutes, to the end of the class, let me show you an application of pebble accretion to solve an outstanding problem. Should be this one, the size-density relationship of Kuiper belt objects. So what is it that you're seeing here? You're seeing objects in the Kuiper belt. This is the mass here, and this is the density, right? These are small objects, right? These are the cold classicals. Most of the objects here are cold classicals. And here you have higher mass objects. You see that there is a bimodal distribution. You have small objects of low density, so small and fluffy. And you have here increasingly higher densities for these objects here that are more massive. So Pluto, Aries, and Triton, right? They have densities that are closer to the densities of silicates, whereas these objects here have densities that are closer to the density of ice. The density of ice, if it's compact, is 1, right? The density of silicates is 3. So what is going on here in this case? Are these objects more compact and these objects are not? Even if you assume that the porosity that you would need to assume for these objects, basically how fluffy they are, would have to be very high. So that's implausible. Is the sample here biased in some way? Are we missing objects here? Maybe these objects exist, but we don't see them, right? Maybe there are high-density small objects. Maybe they're difficult to observe. And maybe there are also low-density high-mass objects, but we somehow don't see them. That's also implausible. And then maybe these objects here, they are more compact because they had the giant impacts. And these impacts will compactify them. But again, it is difficult to imagine that every single one of these would have giant impacts and none of these would. So these 3 possibilities are implausible. And that was hinted at, actually, by, oops. Yeah, that was hinted even here by this this article by Mike Brown saying that even with the additional compression that you have from gravity, the density would still be close to 1 if they're all made of ice, right? The density 2.5, which is the density of Aries here, which is much closer to the density of silicates, and then goes through these 3 alternatives, and none of these appear likely. And then says in the end, the rock-rich larger body may require a different formation mechanism than the rest of the Kuiper belt. That is all unlikely. So how do we solve this problem here? One of the main ideas, I would say, like the current best belt, sorry, the current best bet here is that indeed these objects, they are porous, but you remove it through gravitational compaction. That means that as you grow in mass, right, the gravity by itself will compact these objects. And these are some of the curves here that you get by gravitational compaction. Fm here is the rock mass fraction. So these are curves here of equal rock mass fraction here, half, right, 0.5, 70% rock to 30% ice, and 80% rock to 20% ice. And these are the lines here of fully compact objects, right? So this seems to be fine, right? You can fit several of these objects here with this model. There is a problem, though, here, which I'm highlighting, is that in the early solar system, there was a lot of aluminum-26, which is a radioactive element. And there is a lot of energy that you can get from aluminum-26. Aluminum-26 binds to silicate, so any object that is rock-rich would be very rich also in aluminum-26. If you form these objects here early on, that amount of aluminum-26 would be enough to melt right? And then you simply wouldn't have these objects here on this side of the diagram because the melting would remove the porosity, and they would immediately jump to the density of fully compact spheres, right? So yeah, early melting gives you too much energy that leads to melting, removes the porosity, and then you cannot reproduce this. So what are the assumptions that are going here? That you have a constant composition at birth and growth, and the growth in this case here is done by planetesimal accretion. So these are the things that we are going to attack here. We are going to do away with these assumptions, both a constant composition and also that the growth is by planetesimal accretion. Let's see what we get here if we try to grow these things by pebble accretion instead. Right? So the idea, the pre-pebble accretion idea for planet formation was this one. Right, that you have dust, and you coagulate the dust right through the mechanisms that we talk about. You form the planetesimals, and then you have planetesimal accretion. You form the oligarchs. They grow up to the isolation mass, and then once they form a core, this core either fails to become a gas giant, becomes a ice giant, or then capture gas and become a Jupiter mass object. Now, the constant composition is unlikely because of this this process here that is being shown. So what you're seeing here is a diagram of the particle radius and the height above the disk midplane. And what is going on is that if you have small dust grains that are lofted high up in the atmosphere of the disk, they will be subject to the UV from the star. And that can remove the ice. So you end up with a population of small grains that have ice being removed. And then as the grains grow large, they will settle, right? The scale height is going to be lower if the Stokes number is high. So higher dust grains settle closer to the midplane. They're shielded from the UV from the star, and they can keep their ice. The small grains cannot. So in this way, you have small ice-free grains and large icy grains. Right? So here then you see in green here, they are the ice-coated grains, and in blue here, they are the ice-free grains. You have that the large grains can settle with ice, and the small grains can get their ice removed. Right? So you end up with this bimodal composition. So what happens then if you do a streaming instability calculation with both ice and silicate? So large objects are icy, right? Big grains are icy, small grains are not. So the streaming instability is kicking in. As you see, some planetesimals are forming here. Once you split them into ices and silicates, this is what you see. That the first objects that are forming, the streaming instability acts on the bigger grains, on the icy ones, and not on the small ones. Right? On the silicate, you cannot see any signature whatsoever of the streaming instability. They're all in the ice. Right? So there you go. You started then with the first objects being icy. So you formed the first planetesimals in this range of the diagram. Right? So they seem to explain the small objects that are not compact. Right? So they have the density of ice, and then you give here a porosity to them so that they match the objects that you see. And then how you form these objects here then? That's when pebble accretion kicks in. Right? But even before that, because you form these by streaming instability of ices, you can calculate what is the ice mass fraction that these objects have, and this is the number that you find. Right? They are very, very icy. So the aluminum 26 is binding to the silicates, not to the ices. So you form ice-rich, aluminum-free objects to start with. They will not melt. You can even calculate here how much melting you get. You can go for these equations here. That's the solid fraction, the abundance of aluminum-26, and then how much heat you get from this. And you can go through these equations here and then find out what is the increase in temperature that you expect as a function of the abundance of aluminum-26. And you find that for different abundances here, so these are 2 abundances of aluminum-26 that are given in the literature. For the smaller value, it's the blue curve here. So these are the thresholds of about 250 Kelvin and 200 Kelvin. And then to reach 250 Kelvin, even 47% silicate mass fraction is not enough to achieve that. For the higher mass, yeah, we would have a problem because 6% silicate would already lead to melting. But with the blue curve, then with these ice mass fractions that we find, we are safe. So these objects will not melt. Right. Now the question is then how to grow the other objects. And that's where the pebble accretion comes in. This was core accretion 15 years ago. And the current picture is what I showed before. You have that the dust grains are forming by coagulation. Pebbles, right, will be here, will form. You form the planetesimals by streaming instability of the pebbles. And the planetesimals are growing to planets both by colliding with each other, but also by accreting the pebbles. And in this case, the growth by pebble accretion can significantly dominate. We had to do here in this study some changes to the theory of pebble accretion to include the accretion both by the bigger grains and the smaller grains. But in the end, then what we found was this: is that if you include the growth, then also by the accretions of these small grains, this is what you get. So you form IC first, but you are accreting the silicates in the long pebble accretion phase after a few half-lives of aluminum-26 pass. The half-life of aluminum-26 is 700,000 years, right? The pebble accretion phase lasts for about 10 million years, right? And that's enough time then to accrete them slowly, and then you're safe from the heat from aluminum-26. This is one of the growth tracks, as you see here. What is shown is the ice fraction. You start icy, and then you accrete the silicates. If you accrete pure silicates, you can reproduce Aries. If you put grains of a different composition, allow those grains to also retain some ice, these are the growth tracks that you get. You can reproduce the other bodies. There you go. It passes here then by Charon, Triton, and Pluto. So this was a model that we could reproduce the densities and the masses of Kuiper Belt objects. All right, I guess I'll stop here. If you have any question, I'll be glad to answer them.
Hi. It wasn't so clear for me. How did we pass from the last class, from this one? In the way we were talking about how there are 3 limits for the growth of the pebbles and the grains. Mm-hmm. So I want to know how could they reach the enough size to be our planetesimal?
So what I think that I'm hearing is how do we connect the formation by streaming instability to building rocky planets through pebble accretion, right? Yeah. Okay. Yeah. So if you see here this this mass growth, let me pull here again. If you see here this this mass accretion tracks, a planetesimal, when it forms, is at about this range of masses here, right? So if you form a planetary embryo of about the mass of the moon, that's fine. I mean, like you form here with this mass accretion rate, right? About 10 to the minus 5 Earth masses per year. That is enough to grow a full-fledged planet within the lifetime of the disk. If you form here at this range, like 10 to the minus 4, you are at the onset of Bondi accretion, right? So the accretion rate is going to be about 10 to the minus 9 and 10 to the minus 8. So 10 to the minus 8 Earth masses per year, that means that you are going to grow an Earth mass in 100 million years. You're going to grow a moon-sized object in 1 million years, right? The mass accretion rates, as you see here, they grow quite a lot as the mass goes up. So you can start with an object of 10 to the minus 4 Earth mass, which is about the mass of Pluto. And you would grow in 1 million years to the mass of the moon. And once you are at the mass of the moon, the growth rate is extremely high, right? So about 10 to the minus 3 Earth masses per year. So in 1,000 years, a moon-sized object can grow to Earth mass. Right? So what you need to do is to form objects at this mass range here to start the growth. That's what the streaming instability does. And then once you form these objects, they will accrete the pebbles first at a slow rate, but then the rate will accelerate. That's what I showed in that last animation. Right, you have that the objects that are formed by streaming instability, they are first at this range, right, of masses. And then they start accreting the pebbles, at first at a slow rate, but as they grow in mass, it goes faster and faster. So then you can reach objects of higher mass in this way. Is that clear?
Okay, so the limits that we were talking about yesterday are included in those accretion rates. That's what
the limits.
Yeah, like
the fragmentation limit and drift limit,
that,
right? So these are limits to the growth of dust grains, right? Yeah. So that limits the growth of the dust to millimeter-sized grains. And that is enough to trigger the streaming instability, right? So going back here to the very first plot that I showed in the beginning of the class, the timeline of planet formation, what you're talking about, those barriers, there are barriers for the dust to start growing to the sizes that can trigger the streaming instability here, right? So yeah, the dust growth, right? So you form the pebbles by this way. These are the ones that are limited by drift and fragmentation. But once you form them, you jump them to higher sizes. So through streaming instability, you're going to form the planetesimals. And then comes what we talked about today, which is the phase of a planetary growth, both by planetesimal accretion and pebble accretion.
Thank you.
All right.
I'm not sure if I understood why, in the last plot you show, why the ice fraction decrease when the mass increase.
Right. Right, so your question was, why is it that the ice fraction is decreasing towards the end? Right?
Yes.
So at first, yeah, you see here what is happening. You start icy, right? And then as you accrete, right, the ice fraction decreases, and then here the ice fraction starts to increase again. Yeah, so I glossed over a bit, so my fault. Because what I showed here are 3 different models for the accretion. So thanks for the question that allows me to show this to you. So these are three different models that I tried. The first one is this, right? The passes by Aries, is that the pebbles that are being accreted by the objects, in this case, they are completely silicate and no ice at all, right? What is shown here is the internal density of the pebbles and then the ice volume fraction. In this case, you start with an icy seed that is accreting only silicates. That's why you can build Aries, right? The model 2, that is this one that reproduces Pluto, is this model here. So in this model, you start from pebbles that are pure silicate up to a threshold, and then their ice fraction increases, right? So up to this point, they are silicates, but then here, then they start to become more icy, which is why in the beginning, you are accreting the silicates, but as you reach this region here, they start to accrete ices again, right? This model here is a model that I tried the first, just a simple power law. We all love power laws, right? And it turned out that it does not reproduce anything, right? Because in this case, the accretion is mostly happening in this region of the diagram here, which is mostly ices anyway. So the densities that you get will just be icy, right? So this model here seems to be the best to reproduce Pluto, and this model seems to be the best to reproduce Aries, right? That's why.
Questions? So, summarizing this class, we cannot form Plutos, right? I mean, sorry, Jupiter in the Jupiter position, right? That is more or less your last slide. Simulation stop at Pluto masses. So, second, very sad to summarize from your classes that we have not exoplanets in POP2 stars. So, this is quite bad for us. That is true.
Okay.
These two, I mean, two ideas about the class.
Is it a bit of a stretch?
Yeah. So first, we can grow Jupiter where Jupiter is. True. That's what you see from this. Now, if you see the mass accretion rates from pebble accretion, you are able to get high enough mass accretion rates up to about 25 AU, right? So you would be able to form Earth mass planets up to that region. I'm trying to see here if I have a plot of the mass accretion rate. Yeah. Right. Yeah, like that plot was the mass accretion rate at 5. Yeah, so these are the mass accretion rates at 5 or 10 AU, if I recall. I tested also what the mass accretion rates would be at different regions. Oh, there you go. Yes. No, these are for the different rate. Yeah, these are for different distances, I think. Right. So I tried the same model here for 10 AU, 15 AU, 20, 22, 25, 30. What you see here is up to 22 AU, you can grow objects, right? You can grow Pluto and the other Kuiper Belt objects around this range here. At 10 AU, accretion is too efficient, right? You form objects that are much more massive than Pluto. 15, 20, 22 AU, that's fine, right? That's the window where this model works. So I could conclude from this that probably Pluto formed at around the 20 AU. If you try to form Pluto at 25 AU or 30 AU, you see here the mass accretion rates are just too low. You don't grow objects that far out within the lifetime of the disk, which fits, right? We know that the cold classical objects in the Kuiper Belt did not grow to Pluto size. So what is the conclusion that one draws from this? Pebble accretion seems to work up to 25 AU. Beyond that, if you form planetesimals, they will remain planetesimals, right? So that explains the Kuiper Belt. Now, the second part of your question is population 2 stars. How was that jump?
Again, I mean, I'm just summarizing the big problems of the models, right?
Right.
One is Jupiter over there,
Right.
and exoplanets in POP2. So I thought kind of summarizing of limitations. let's
Right.
say.
Yes. So the population 2 case would be, as we talked about on the first, on the class yesterday, about the streaming instability. Exactly, yes. It would be a problem to form planets on the population 2 stars if you need the planetesimals to form through streaming instability. That is true. That would be this case here, right? Yeah. So what this plot was showing was this, that in the green region, you can form planetesimals. In the pink region, you can't, right? And the metallicity that you have here barely is under 10 to the minus 2. So this is the metallicity of the sun, right? If you go to 10 times less, you are in the area of no strong clumping. But again, the two things about this. We are still working on this figure. As I said, come back in 1 year. This plot's probably going to be different. And another thing that I didn't touch upon is that there are other ways to form planets. Actually, my favorite way, which I didn't talk about yet, I was going to talk about the next class, is by vortices. This is an observation, right, of a disk. This is the disk around the star rho Ophiuchus, IRS Ophiuchus 48, and this is MWC 758. These blobs here that you're seeing, they're dust, like large dust grains, pebbles that are being trapped in what appear to be vortices, right? And these vortices are very good to trap dust. And I don't want to give a full class about that now since we need to go to the coffee break. But long story short, you can actually form very big objects very fast by trapping the dust in these vertical structures. I just published actually a paper that shows the planets that you find in this case. So this is planet formation here on this vortices, and you get like very high mass planets actually approaching the mass of the Earth. And I don't have here a plot that I tried also for different metallicities, and I can make this scenario work even for metallicity 10 to the minus 4. Yeah. Okay.
Some hope.
Okay, so all the simulations that you showed us were like for mixed silicates and ices, right?
Mm-hmm.
So I'm guessing like these simulations, and you showed us, are in order of like 10 astronomical units. So we aren't like really able to explain information of Earth, Mercury with them. Like we're working with the outermost part of the solar system. So how can we form like? Is that true? That we would have a mix of silicates and ices at low astronomical units.
Right. That is not completely true that these assume both ices and silicate. That's for this last model that I showed. But these accretion rates here, so these accretion rates that I was showing before, let me pull them up again. They do not assume ices or silicates, right? This here does not assume that it's either one or the other. Ices or silicates, in this case, they will come in the picture by either, by what the fragmentation speed is, right? But once you form the pebbles, the streaming instability will work in the same way for both. So for this case here, yeah, it was assuming the fragmentation speed of 1 meter per second for the silicates and 10 meter per second for ices. So that led to the idea that maybe it would be much easier to form planets with ices, right? Because the fragmentation speed of ice is much higher, right? They would stick to each other in a better way. But in fact, there are some recent laboratory experiments that show that that's true that ice sticks well, like in this temperature here. But if you go to the temperatures of disks, about like 20 Kelvin or so, then ice will behave pretty much like silicates. Like in the distances of the Kuiper belt or so. ices and rocks, they would behave in pretty much the same way. But then in the region where the Earth is, yeah, you don't have ices, you only have the silicates. And in the region of the Earth, in fact, the accretions the accretion rate you get from planetesimal accretion and pebble accretion is pretty much the same. Yeah. Coffee. Okay, thank you.